This meeting is being recorded.
네, 칸도 하고 하나 합니다. 이 프로그램 그래라 그랬던 것이 홈터에서 메타서 홈 되게나 마시신 메타네 파스 포지션 메타네 아주가 미트는 램슨 메타네 거 홈터에 맞다. 시 도비지나 세컨 메타가 그리고 सक्सेसिव एप्रोक्सीमेशन मेथड का जो हाई बनिस तवताना कोई इटरेटिव मेथड लोरेगो अदना हानई खंगबा यावदी हायो मखा तकदरगो ꯅꯪ ꯈꯪꯗꯕ ꯈꯣꯠꯇꯕ ꯌꯥꯎꯔꯒꯗꯤ ꯍꯥꯏꯔꯛꯑꯣꯀꯣ ꯍꯥꯏꯔꯛꯄꯗꯤ ꯌꯥꯝ ꯐꯔꯦ ꯉꯁꯤ ꯇꯧꯗꯣꯏꯁꯤꯅ ꯑꯩꯈꯣꯏꯒꯤ ꯅꯍꯥꯟ ꯇꯧꯒꯅꯤꯗ ꯔꯦꯞꯁꯟ ꯃꯦꯊꯗꯇꯣ ꯑꯗ ꯑꯩꯈꯣꯏꯅ ꯀꯦꯟ ꯋꯤ ꯌꯨꯁ ꯗꯤꯁ ꯃꯦꯊꯗ ꯐꯣꯔ ꯇ꯭ꯔꯥꯟꯁꯦꯟꯗꯦꯟꯇꯦꯜ ꯏꯀ꯭ꯋꯦꯁꯟꯁ ꯍꯥꯏꯕꯀꯣ ट्रांसेंडेंटल इक्वेशन की ngसाई हाइवा हाइपरबोलिक साइन कोस एक्सपोनेंशियल याव फंक्शन दो अदु फंक्शन याव दो हाइपरबोलिक कैटेगरी ट्रांसेंडेंटल इक्वेशन को नता सपोज अखोगा सोन पे को e to the power x plus x equal to 4 in when we know now how to find out the root for such equations have got such type of equations is known as transcendental equation ko इसलिए कि साइन याव कोस याव नता hyperbolic function all belong to transcendental equations. In such case, what shall we do? You see here, this is a given equation. So what happens? We just bring in here like this. Now what happens? This becomes my f of x. So we can write f of x equal to 0. So from this, what happens? This should be my f of x, right? So using Newton-Raphson method, what we need, we are going to find out the differentiation of the given function. So just to find the differentiation, what we do, we calculate like this. For e to the power x, this should be remain as it is. For x to 1 for constant, it turns out to be 0. And this is the formula for Newton-Raphson method. In this method, what we do, we need one starting value x0. Once if you know how to get this value, then we can find out the value of fx. By substituting to the given function here, then we can find out the derivative of the function by substituting the value of here, right? But in my last class, I explained you how to choose the starting value. So if you don't know how to choose the starting value, then you cannot convert to the required root, right? So you may get diverse or you cannot get what you want. Now,
Sir, X not choose to them to hal have you
X manga aina hayuga yahuga
Hey Yahoo sir.
Of course, from the given graph, from this graph, where is the root? My root is nothing but it is point. This is my root. This is what we want to find out. Means when the value of fx is 0, then the corresponding value of that x will be the root. Now, in case of this Newton-Raphson method, what happens? How to choose the starting value? We can choose here, somewhere here, anywhere. So what happens? Randomly, I consider 4 points. The first one is this x not 1. Suppose if we consider here, that's just nearby the root, then what happens? In this case, what happens? We are going to draw a tangent, right? This is depend on the slope. So what happens here? By drawing a tangent here, then after that, what happens? We can come again and we can convert to the root. Okay, using this formula. Now, suppose if I far away from the root, then what happens here? When we draw a tangent here, this will come here, right? For the next point, what happens? We are going to do a tangent at the value of fx. So in this way, what happens? This will go diverse. We cannot come here. So if we choose in far away from the point, then we cannot get what we want. Similarly, there's somewhere here, just we consider here f03. This is very far away from the root. So in this case, what happens? According to this graph, suppose let us say this is my starting point. And what happens is then here we draw a tangent. And for the next point, what happens? We are going to draw a tangent like this. So if the graph turns out to be like this, then what happens? In this case, this will go ahead and final loop, and it cannot come here. So we cannot get what we want. Similarly, suppose we consider here, now let us say this is our another new point, starting point. Suppose let us say this is f04. Here I consider here what happens when I draw a tangent, this will draw here, then what happens? We cannot come here. So the solution is that suppose if you want to converge to the given root, then the best way is that we should choose the starting value near the root. हाबदि रुटुगी मयादा अपने starting value लोगों को हाबदि ये converge to start to one है. So now we are going to see using this for happen. Now how to start with this? Now this is our given function, right? This is our equation, and this is our derivative. Everything is with us. The question is that how to choose the starting value, right? So now if we don't know how to choose the starting point, then what happens is actually it may get diverged. So what do we do? From the here it is for 0, suppose it is for 1, let us say. It is for 1 is what? 2.7 something like this. And what happens? 2.7 something plus x. X is 1. So we can start 1 as our starting point because we know the root will be something around the 1, like, right? Because this will be 2. When x is equal to 1, this should be 2.7 plus 1, 3.7, so it is equal to 4. So what happens? We can choose our starting point as 1. You can say 1.1 or you can say 0.78. But then we can choose nearby value. So if you take -5 or -10, then we may not get the required root. So now let us see the process how to find out the root using the Newton-Raphson method. This is for transcendental equation. In our last class we have done for algebraic equations. So now what happens using 1? Let us find out f of x naught. Just to find out f of x naught, we are going to substitute here. When the value of x naught here we choose as 1. So substitute here 1. So this should be 1, right? So substitute 1 here. And how much you get here? So you will get something like this, minus 2.78 like this. Okay, so yeah. When x is equal to 1, e to the power 1, e to the power this is equal to e, right? 1 plus, so what happens? We got this one, minus 0.2817, something like this. Now, what happens is just I keep here, right? Then what happens? We're going to find out derivative of the function because to find out the next root, we're going to use this formula. So from the given formula, we know f x naught. Now we find out f of x naught. Then we're going to find out f prime x naught. So to find out this derivative, we have already calculated here. So substitute x1 here. So e to the power 1 plus 1. So how much you got it? You substitute like this. E to the power 1 plus 1. So it is 3.71 So we just put here 3.71 Now using these three values, we can calculate the next value. So the next value is 1.07576. How we calculate it? We can substitute here. This is x1 is equal to, this is our formula. So we substitute here. x1, x0 is 1. This is our starting point. Minus f of x naught is minus 0.28172. And f prime x naught is 3.1719. So after this calculation, say let us say we got 1.075. So I put 1.075. Now, I hope you understand this line. Okay. For bisection method and the false position method, what we did, we checked the sign of the given functions of f of x naught and f of x2. If they have same sign, then we assign the value of x2 to x naught. Otherwise, we assign x2 to x1. But now, in Newton-Raphson method, we don't need those things. So what happens is we go this, using this x naught, we find out x1. So for next iteration, what shall we do? Simply the value of x1 will be assigned to x0. Okay, then what happens? We are going to calculate again new this x2 like this. So what shall we do? Now this will be our new value of x0. We can say x. Now this
Sir.
here.
Sir,
I don't, ah,
1 gidane x not to 1 law do it can be beludo.
any starting point no one of them.
Oh,
When approximate allocation one ever, when the same location that is not 0.75 I guess you guys did it. Minus 5 yam chow low, when the high sneak while on the given equation, you must draw quite a game of the DC. See, for see, while looked at the 2.7 plus 2.7, almost 4 minutes. ಅದನ್ನ ಸ್ವಲ್ಪ ವಾಲೋಷನ್ ಮಾಡಿ ಅದನ್ನ ನೋವು ತಮ್ದ ನಿಯರ ವಾಯ್ಸ್ ಅನ್ನತ ವಿಧಾನ minus 10 का plus 10 option होती कोई ना होगी फिर उसे बहुत है ना उसको कन्वर्ट ऑप्शन क्या है होगा
oh, siya kangan.
now मतलब ना कहते हुआ I think you understand this line okay then what happened we are going to calculate the relative error for our just for a stopping criteria. So what happened? You substitute the value of this x1 is nothing but this one, x1 minus x0 is this, and this is the definition from relative error. So here we calculate relative error. Okay, here I have written here. This is for programming and for terminating criteria. How to terminate our loop. So for the next iteration, what shall we do? Just if you cannot understand the first line, you look at here again. Now, the value of x1 now turns out to be x0 for our next iteration. So, using this value, what happens? We substitute to x0, f of x here. We substitute here to get the value of f of x. Similarly, so when I substitute here, you calculate yourself, you may be getting like this. Yeah, this is what you get when you substitute the value of x is 1.07. Similarly, again, just to find out derivative of the given function, you substitute the value of here. Then we find out the derivative of this function, right? So in this way, we calculate these three. Now we know these two values. Then using these three values in the given over here, you substitute here. Then we can find out the new x1 here. So x1 is here again. So here, as I told you, in this case, only for checking the sign of the functions. Directly, this new value will be again the new value of x0. Yes, similarly, we are going to proceed here. So how long we are going to proceed here? When we can get two terminating criteria. The first one is we can see in the programming part what happens. We are going to check through the relative error. If the relative error is greater than or less than 0.0001, then we can stop our criteria. Or what can we do? In the second case, what happens here when the value of fx is almost 0? This is almost 0, right? If the function this f of x is almost 0, then the corresponding value of this root, value of x will be the root. Okay, so what happens? There are two ways for terminating criteria. When we calculate the value of fx, it is almost 0, then we can stop our iteration. In the second case, what happens? The easiest way is the programmer, we are going to use the condition for this relative error. When we calculate the relative error is nothing but the difference between the old and new points, right? So if the error is less than 0.0001, then we can stop our iteration. Means the values are almost same, right? So we can use two terminating criteria. Now, let us see. What is the algorithm? Yesterday also I have shown you. Algorithm is very simple. Now we are going to start the starting value x0. Related error maybe 0.001 or anything something like that. Then here number of iterations. Suppose by choosing a wrong starting value, then what happen? We may not get our result. So what happen in such case? Our program may go and for an infinite loop. So what happen? We can put a terminating criteria in writing our program. So let us say, please check for 20 times. If we cannot convert to a root, then come out from the root, right? So in that way also we can provide one terminating criteria. Because in this case, for example, we need only one starting point. If we choose a wrong or if we choose a wrong starting point means then what happens? The program may go for another. So that's why I suggest you to choose the route nearby, to choose the starting value nearby the route. So now here in our programming part, we are going to put some maximum iteration, maybe 20 or 30. If we can converge before this iteration, then we can stop it. Otherwise, after doing this maximum loop, then we can terminate our program also. So I will show you here. Now here let us say this is the condition. So what I am saying that n may be 20 or 30. So I want to continue my loop to, so let us say n go to 20 times. So I want to continue these loops for 20 times. If we cannot convert the loop, then we can stop our iteration. Okay, this is one terminating criteria. Second is, what happens? Suppose here I calculate the value of this derivative. Okay, here what happens? If the slope is very small, then what happens? We cannot calculate, we cannot give the chances for divergence is very high. So what happens? We say, right, slope is very small, and when the values at slope was right, then otherwise suppose now this is another criteria. If the related error, what will be calculated less than the provided error, then what happens? Go to 30. 30 means here, right? Or conversion route and find the value of x effects like this. So what is saying? Now suppose let us say after 3 iterations, if this condition is true, then automatically this will print this message. The route is like this. In this case, what happens? No need for continuing up to 20 times or 30 times. So what happens in this case? We have to provide two terminating criteria. Mainly, this is first one, and second is from here. Okay. Another one is it happens if the slope is very small. If the slope is very small, what happens? We cannot calculate this one. Suppose let us say if it is very small, then this is very right. Then what happens? This will be very huge number. Then what happens? Program will crash. So if the value of this appliance is very small, then we can print a message and then we can terminate our program. Okay, this is the now. Let us come to our programming part. Okay, so what happens? As I told you again and again, these portions are actually same, right? Nothing changes here. So what happens here? This will find out the range of the roots means from the given root. But what happens in iteration method? This is needed for what? These things are required for algebraic equations, and but for these transcendental equations, I think we cannot do like this, right? No need for this thing. Now this one is for our this is for now. When us here. Now what happens in this is for algebraic equations, not for the one we consider here right now. This is not for transcendental equations. So here, what should we do? Now we initialize this. What is the meaning of this? Okay, actually this should be your assignment. So what happens? I am telling you, this is for algebraic equation. Once you know very well about this algebraic equation, you can change for any equations, maybe transcendental equation. How to change it? You can change here, right? In my case, what happens? This is simple algebraic equation. If you understand this program, if you simply change here, right? Then other part no need for changing too much. So see here, what is the value of this z? Here what I am doing, simply I assign the initial value of z is the value of a. So what is a? Again, let us see here. What is a? A comes from this function here, right? See, this is the value of a. So this is nothing but the starting value, right? And this is our allowed error. So in our case, let us say in this given equation, it may be either 0, 1, -3, -2, that's whatever we have done here. So whatever it may be, this will the value of A will assign here, right? Similarly, using this A, we calculate the value of fx here and we assign it here. So we got two values, starting values. This is for just for printing, right? The print I with 5 space and print I in the right side. Similarly, we print x, fx, and so on. Now, this is the see, this is 2. 2 means what? This should go for an infinite loop. So, how to terminate from this infinite loop? Now, let us see here how we calculate x. So, just to calculate x for a fun, we use this one. Or the value, this is the all values of x, right here. Then this is f of x and divided by this f1 is nothing but the derivative. So, we calculate x. So, this value x I again assign to z. Similarly, again, we calculate assign to fx, or fx at z. Thus, we attend one by one. So, this will continue again and again until this condition is true. Right? If this condition is true, means the value of ERR is nothing but how much? 0.001. So, if the value is less than this, then you break out from this loop. Okay, then print the values. Okay, this is for simple Newton-Raphson method. But if you want, suppose let us say, for transcendental equation, as I told you, instead of giving directly here, it is better to use one loop. So say let us say for I equal to 1 to 20, something like that. If do you know why? Because if this condition doesn't come up, okay, even in this case, if this condition doesn't happen, then what will do? This loop will go for an entire loop, right? So we cannot come out from the loop. So the best way is that in case of transcendental equation, instead of using like this, so instead of going for an entire loop, simply better to use a loop for a limited this condition iteration. So let us say for I equal to 1 to 20, 30, something like that. If we cannot converse to the defined iteration, then we can say that come out from the loop. Okay, so what happened here? The best way is that the better to use a finite iteration. Ko, si yengo, yung si tarake ko, si kanda, pero to you are going to write a program for transcendental equations for solving, for finding the root using Newton-Raphson method. Sini ruwa, sini algebraic equation ini, nene to how to convert it to a transcendental equation. Actually, you send here, natasina send to wilani, and the good somewhere here, stamina send to. For any good then I take send to that. So it's solution man to be are for. Sigi so mayam jima, apna transcendental equation di kanan re for alang to be kata. But to tare for. Okay, now let's come again to the second method. Hello,
Sir,
okay, but how?
sir, hajiki program the return to muto. Return to the mic, but the command in the UP utters. Okay.
Actually, the campus space is simple. And the, of course, either Karigumba, Sigi Beruze, Shana, either Sigi Beruzi, she print the Hungary, and a return has a jet nor Thomas and print the Hungary. I just already princess to Hale. So, there ain't a problem, don't want to see you to shit over. So, she thought the root is another, and well, the root is cancelable. So, China, between had a record, spelling in some way that she had had record. And I had this one to the print of it. Having a Sagi, a print of palm, who is the print of a for. That is the young was the Chumakanda, she threw a kanda print of Ineva. Other than the Hajikano. Sagi compare the 106 of Sheko, sing Jena as the print of Manan. Other in Hajikano, they see there is a return to Hungary, 10,000 for big tattoo flavor. And suppose is a return na Hapaga, jet, I mentioned return to Hungary. Sigi Sarukshi, Aina, Makari, the print of the action, the print of VI. value में assign तौꯁꯤꯜꯂꯒ ꯃꯃꯥꯡꯗ ꯑꯩꯈꯣꯏꯅ ꯑꯇꯣꯞꯄ ꯌꯥꯝ ꯇꯧꯋꯤꯗꯥꯏꯅꯦ ꯀꯔꯤꯕ ꯑꯩꯈꯣꯏꯒꯤ ꯁꯤꯗ ꯇꯧꯗꯥꯏꯅꯦ ꯃꯇꯤꯛꯁꯤꯡꯗ ꯇꯧꯕꯗꯣ ꯁꯤꯗ x ꯇꯨ ꯔꯤꯇꯔꯟ ꯇꯧꯋꯤ ꯁꯦ ꯔꯤꯇꯔꯟ ꯇꯧꯔꯦ ꯔꯤꯇꯔꯟ ꯇꯧꯔꯀꯥꯟꯗ ꯑꯩꯅ ꯀꯩꯗꯧꯔꯦ ꯁꯤꯗ ꯑꯃꯗ ꯍꯥꯞꯆꯜꯂꯦ ꯑꯩ ꯁꯤ ꯁꯥꯏꯅ ꯄ꯭ꯔꯤꯟꯠ ꯇꯧꯍꯟꯕ ꯁꯤꯁꯨ ꯌꯥꯏꯑꯕ ꯑꯗꯣ ꯉꯁꯥꯏꯒꯤ ꯑꯩꯅ ꯉꯁꯥꯏꯒꯤ ꯁꯤꯒꯤ ꯃꯦꯊꯠꯁꯤꯗꯅ ꯀꯩꯗꯧꯒꯦꯅ ꯍꯥꯏꯕ ꯃꯇꯝꯗ ꯑꯩꯅ ꯁꯤꯗ ꯃꯅꯨꯡꯗ ꯄ꯭ꯔꯤꯟꯠ ꯇꯧꯍꯟꯕ ꯇꯥꯔꯦ ꯀꯣ ꯃꯅꯨꯡꯗ ꯁꯤꯗ ꯄ꯭ꯔꯤꯟꯠ ꯇꯧꯍꯟꯗꯕ ꯔꯤꯇꯔꯟ ꯇꯧꯍꯟꯗꯕ ꯑꯗꯨꯅꯅꯤ ꯅꯣꯏꯅ ꯔꯤꯇꯔꯟ ꯇꯧꯔꯤꯁꯨ ꯀꯩꯁꯨ ꯀꯥꯏꯗꯦꯀꯣ ꯁꯤꯗ ꯁꯤꯒꯤ z-1 ꯚꯦꯂꯨꯁꯦ ꯔꯤꯇꯔꯟ ꯇꯧꯏ z ꯇꯧꯒꯦꯔꯥ ꯑꯃ ꯇꯧꯒꯦꯔꯥ ꯑꯃ ꯇꯧꯔꯒ ꯁꯤꯗ ꯔꯤꯇꯔꯟ ꯇꯧꯍꯜꯂꯒꯅꯦ ꯁꯤꯗ ꯑꯩꯅ ꯁꯤꯗ ꯀꯟꯚꯔꯠ ꯇꯧꯔꯅꯨ ꯍꯥꯏ ꯌꯥꯔꯕꯣ
Yani sir.
Next is second method call. So why we need second method? We have one disadvantage for linear regression method. So the disadvantage is that we are going to find out the derivative of the given function, but sometimes it may be very difficult to calculate the derivative, right? Suppose it requires x plus sin x, something like that. So sometimes it's very difficult to calculate the derivative of the given function. In such case, second method is used. Okay. So what second is suggested is that instead of this derivative f prime x, what we use in our interception method, it is better to approximate it using this definition. Okay. And this derivative substitute like this. F of x and the x minus 1 are two approximation of the root. So using this definition, what happens? We can modify our intervention method, and that method is known as second method. Okay, now you just remember this one. F prime x, instead of this, what happens? We shall use this one. Okay, f of x minus f of x I minus 1 divided by x I minus x I minus 1. Okay, this will be x I. So, I will go. So what happens here? We substitute here. Instead of derivative, we substitute here f of x I minus f of x I minus 1. I and the I minus 1 are to the two approximations to the root. Then what happens? Just we do some simplification. Bring out this one here. Then we can write like this. Then what happens? Do some simplification. Using LCM, we just put here, multiply here, and do something. And what happens at last? You got this one. Okay, now this is the formula for second method. Now you can compare this formula with false position method. Formula will be exactly the same. Okay, so when you use the formula in false position method or regular falsity method, what happens for finding the value of this x new x, we need four values. What are they? I minus 1, x I, right? X I minus 1, then f of x I, f of x I minus 1, like this. So once if we know these four values, then we can calculate the new x values. Similarly, I think this is the formula is exactly the same as before, like we have done in our this false position method. Now, let us say here, just for simplification, if you put I equal to 1, then x2 is equal to how much? X0, I minus 1, we substitute the value of I as 1 here, then we will get like this. X0, f of x1 minus x1, f of x0 divided by f of x1 minus f of x1. So formula is exactly the same, right? Then, now the question may come up, what is the difference between false position method and second method? Okay, this is very important from the point of examination view also. Formula is exactly the same. Here method for process is different. Now let us see here. Okay, whatever I have noted down here, you can make simple notes here. The difference between the false position method and second method. Okay, formula is same as I told you again and again, but there are other differences. Okay, now here let us see here. What is the geometrical interpretation of second method? So what happens here? We need, in this case also, we need the starting point, right? Just like we have done in false position method. So what happens now? Suppose let us say, so please listen carefully. Now we need to starting point. Let us say x0 and x1. Okay, this is our x0. This is our x1. And now what happens from the graph? This will be our required value, right? Just to get this value, what we do, we use the starting point x1 and x0. Then we draw a tangent to this f of x0 and f of x1. Okay, here we draw a tangent here. Then what happens? This point where it touches in the x-axis, is the value of new x2. Okay. Now, how to proceed for the second time? Now, the difference between, let me tell you one point, the difference between this false position method and second method is that in case of second method, what happens, we no need for checking the sign of the functions like we have done in this false position method. What we did, we checked the sign of the f of x naught and f of x2. If they have same sign, we assign the value of x2 to x naught, and otherwise we assign x2 to x1, right? So here what happened, no need for checking the signs of f of x naught and f of x2. Now what shall we do? Now we got this x2, right? This is a new x2. Then what happened, using this x2 and x1, okay, we're going to draw a tangent again through their functions. Say suppose let us say this is my f of x1, this is my f of x2. So now what again, you draw a tangent here, okay, passing through this. Okay. Okay, now what happened, this is again our new x2. Then now we can calculate the new f of x2. This f of x2 and new this x here, you draw a tangent like this. Okay, similarly, by continuing in this process, what happens, we can come to the root. So the difference between these 2 points is that number one is that what happens in this case, we are not going to check the sign of f of x1 and f of x2. Then another point is that just for showing here, what happens, I enclose the root here. This is my root, and what happens, I choose two starting points, x1 and x0. But basically what happens, if you are using this second method, then no need for closing this root. So you can choose our x1, x0 and x1 during this root, or well, in this case what happens, this is not mandatory to enclose the root between x0 and x1. It may be outside also. So there is a difference between false position method and second method. In case of false position method, it is a must that your two starting point x0 and x1 must close the root. But in case of second method, it's not like that, right? You may choose outside the root also, no problem. And second difference is that, as I told you, in this case, in this new method, second method, we are not going to say the sign of the functions, whether they have same sign or different sign. That's not necessary here. But we have to say the signs if we are using the transposition method. If they have same sign, then we assign the value of new x2 to x1 and x1. Now, let us see here. Now, so yeah, thus I mentioned some points here. What are the difference between these 2 points? So, as I told you, in case of false position method, it is we should enclose the root, but in case of second method, it is not need to enclose the root. Yeah, this is a little difference here. And another important is that in case of second method, this is faster. Okay, faster. How to check it out? We can check very easily by counting the number of iterations. Suppose if when you use say for a same equation, it takes about 6 iterations. Then if you are using second method, then the iteration must be less than 6. Right? If the iteration is more than that, then we can say that is faster than our transposition method, right? So very easily you can check it by just checking the number of iterations. And what happens? Second method is faster, but may not converge to all the rules. Whereas if you are using false method, it is slower, but it is guaranteed convergence. Means at least if you are using false position method, definitely you can get the rule. But if you are using second method, that doesn't guarantee that you should get the rule. Yeah, there is some difference here. Now let us see here how to proceed for our calculation. Simply now in this case also we need to starting points. Then error delta, I think there are some errors. Means suppose delta we normally use for small slopes. And what happens, this n is for number of iterations and ERR is our allowed error. Let us say 0.0001, something like that. Now, here, what happens, using the two starting point x0 and x1, we calculate f of x0 and f of x1. Right? Then what happens, I told you that this second method is invalid. It may not include the root, so it is necessary to put this root, because if we cannot converge to the root, then we can come out from this loop automatically. So after, let us say, after suppose if you assign n is equal to 20, okay, let me come again after this one. My times over.
This meeting is being recorded.
There we go. Oh, okay, now, in this case also, as I told you, we need three starting points. So now let us suppose x0 and x1 are two starting points. So using these 2 points, we calculate f of x0, which is represented by f0, and f of x1, yeah, I just denoted by f1. So here, why I am using this loop? Okay, suppose if we cannot converge to the given root, then what happen? Our program will go for an infinite loop. Just to come out from the infinite loop, it is necessary to put a loop. Now, suppose let us say if this loop continues for 30 times, and if we cannot converge, then we can come out from the loop and we can put some message. Okay, cannot converge to the loop. So this is first terminating criteria. Second is what? Now, what happened here? I am just calculating this value. If this value is very small, then you stop the calculation. Why? Because f of f naught, f1 minus f naught, you see here in the given formula, it's here also, right? Here. If the value is very small, then what happens? If the slope is very small, then how happen? You will get a very huge value, right? So immediately, no need for continuing again. Suppose if they are very small, then we can stop our iteration. That's why delta we can define 0.001, something like that. If the value is small, then go to system. Go to system, nothing but this is again another termination criteria. So here we just slope too small and stop the iteration. Here you print the value of x naught, x1, f of x naught, and f of x1, and the number of iterations I. How many iterations you perform, you print all the informations here. Okay, now then if let us say if the slope is not too small, then calculate the value of mu x2 using this formula. Then here you calculate f of x2. Then what happens here, as I told you, no need for checking the sign of the functions. So when we calculate this, if the value of f of x2 is very small, is almost 0, then you stop the iteration, go to number 18. 18 is nothing but here they are all conversion roots, and the value of x2 and f2 are as follows. Okay, so just to print it out. So this is again another terminating criteria. So what happens otherwise in this method, what we do, we assign f1 to f0 and f of x2 to f1. So in this case, no need for checking the sign that we have done as we have done in bisection method or false position method. In that two methods, we normally check the values of those functions and we assign the value of x. But in this case, what happens? No need for checking the signs of f of x0 and f of x2. Simply assign the value of x1 to x0 and x2 to x1. Similarly, you assign the value of x1 to x0 and x2 to x1. Okay. So we are going to proceed this way. Now, let us come again with an example. This is our example. This is what we consider. This is our question, and this is our given function. This is our function. Right? So what happened here? So we need two starting points. So let me take 0 and 1. So now you please see here very carefully. This is 0. This is my two starting point, 0 and the 1. So what happened? Then I calculate this one. This f of x1, f of x1, and f of x2. Okay. Now using this x0 and x1. Okay, these two are the starting points. I'm just making this table in another way, not in the way in the can be. So you choose one. This is the first iteration. So my two starting points are 0 and 1. Then what happens? I find out f of x0 and f of x1. So with these four values, I can calculate x2, right? Because x2 is nothing but here. X2 is equal to that from this formula. So once we know these 4 points, then I calculate this x2. Right. Now, then I calculate in f of x2. Then for the next iteration, as I told you, what happened? The value of this x1 will assign to x0. So we know for checking the sign, simply you assign directly. Then the value of x2, this x2 will assign to x1 here, like this. Okay. Now, so what shall we do? Then we know x0 and x1. Then you calculate again this f of x0 and f of this x1. Then again you calculate x2. Then f of x2. Okay, so similarly, we are going to proceed in this way. So how long we are going to proceed it, right? So as I told you, we keep two conditions. The first one is using the iterations. Suppose if we cannot converge to the root, then we can come out from the loop using our iteration. Second one is that what happen? We are going to check the value of this f of x2. This is almost zero, right? When the value f of x is almost zero, then we can stop the iteration. So here, what is the termination criteria is here given here. When the value of f of x2 is almost zero, then corresponding value of x2 will be the root. Now, this is theoretically, this is the idea. Okay, now what shall we do? How to implement in our Python? Now let us come here again. Okay, you see here, this is our given function. Now I write a function here. Okay, so in this case, what happened? I need two starting points, x0 and x1 as before. So I assign it here. And for f of x0 also, I calculate it here. Okay, other calculation, I assign it to a list. The name of the list is fx. Here, the list is x. So what happened here? Let's I put the condition here. This is the allowed relative error. So if the value of this is greater than this 0.001, okay, then what happens? You calculate this. Calculate the value of this using the formula, right? Then assign fn to x. Similarly, we calculate f of x2. So what happens then? We print all the values. Then we increase I by 1. How long we are going to continue this? Until this condition is true. Okay. So here also what happens? Actually, I should use a loop also, right? So for this program, okay, this function is a very known function. We know that we know all the roots. So suppose if we want to generalize this program, then instead of this while loop, what happens? We should mention to the for loop, so that after some iteration we can stop our program. Suppose in this case, if you cannot get your root, then what happens? This will go for an infinite loop, right? So the best way is that we should pick one root of one loop also. Now let's see here how you do it. See here. Now first one, it comes to four iterations, right? So similarly, what happens when you calculate, when you use the False solution method, you compare the number of iterations. This will be less than that, right? So this is the first value. For the second value, when I use 0 and 1, we calculate this. Okay. Then what happens? This is the starting point. So yeah, we got only 4 iterations like this. So adana hujik logba is very simple one kwa. Adana hujik mina tawudi shi kainam tamda sijo kena logba. We can keep all this loop inside the loop. Naka sini amje loop na sun bayo. How you can we know? Karigamba when the loop converts to one amukta our program will go for infinite loop. She doesn't kill any. So she doesn't kill any. She special to go the this will go for infinite loop. So just to control it, what happens? It is better to assign a loop. So inside a loop. Sign a title. From then happy mana, nama happy ahead. Now so ina fiyo kan sanje. Se hasan se swaina. Ay so fiyo. Kan na se rigyan method mai sila khang do yaw de ko. I next topic will be my successful approximation method using ko. Aduna khang do yaw de haro. Successive approximation program method ni ko. Aduga mathang lei koi system of simultaneous equation hawrani nata. Aduna yarige noi jena khamda tara bogi man so tak ta hawung no leno hona ja de ko. Aduna je khawda khang ko to yaw de haro ko. Before I proceed further. People recording and look bro. Any come there?
Nung kang isa.
The last topic is successive approximation method. Especially this method is used for solving our transcendental equations. So, ang transcendental equation ni kayo, sa ina higher na ta. Suppose, let us say this is our given equation. So, from this, now let us say this is our f of x. F of x is nothing but infinita. Now, how to solve this? So, as we know that, suppose if you want to draw a graph in Python, you can draw it very easily, right? But now, suppose let us say, let us draw it manually, e to the power minus x will be in this way. So, the plus one only now, suppose starting point when x is equal to 0, the maximum will be 1. So in this way, we do a graph like this. Now, then what happens in this case, this graph will not touch the x-axis. So it will not cross x-axis. But how to find out the root? So the root is what happens, we draw a line x y is equal to x. So what happens, this point, this intersection here is the root. Now, this is the theoretically, this is the way how it calculates. But now let us see how to implement it. Now let us say in this case in this diagram x naught is our starting point. So this is corresponding f of x naught. Once if we find out x naught, then what happens? We can find out x1. Okay, by calculating from this point, we can calculate again x1. Okay, let us see how to do this one. Simply, it's very simple. Now, in this method, let us say this is our given equation. So, for example, here we are going to express like this: x is equal to gx. So, what is the meaning of this? So, now just you put x for not this one. The easier x, you just put in the left side. The remaining functions terms, for remaining terms you keep on the right side. So, from this given equation, can we write like this? From this, can we write like this? X is equal to 1 plus e to the power minus x divided by 2. Okay, just we have converted like this from the given equation. You keep x only in the left side, the remaining terms on the right side. Now, as we know that the root of the equation f of x is where at this point is equal to this intersection, we are going to find out this. So, how to proceed this? You see here, very simple. Here also what happens? We need one starting point. There is nothing but this x naught. You switch x naught, then you substitute to this g. Then what is g? You see here, this is our given function. Now, as I told you, x equal to gx. Gx is nothing but x is equal to gx. What is gx? So this term, when we put x on the left side, the remaining term on the right side, so this term represents our gx, new function. Okay, so you substitute the value of x for you choose the starting point value here, you substitute here. If you substitute here, then what happens? We will get the new value of gx. So in this way we calculate g of x, we assign to h1. Then again using the value of x1, you substitute again to gx, then calculate again new value. Then this new value again you substitute again in the gx, and this way what happens? We are going to proceed this way. So how long we are going to proceed here? Here also what happens? We are going to use our relative error. Using the relative error, if the values of this cumulative values x2 and x3 are almost same, then we can stop our iterations. So here, what I do, I choose the initial point as -1. Then what I do, I calculate this gx. Okay, gx I calculate here, and what happens? This is our relative error. Okay. So similarly, then what happens? This value of whatever you calculate here, this will be again the new value of my x. Then I calculate again gx on 5. So where we are going to stop it? When the value of this relative error is almost 0, then the corresponding value of this, so this dx, whatever you call this will be our value type. Okay, here also what happens, choosing the starting point is very important. Now suppose let us say here this is our root. Okay, this is what we want to find out the value of this in the intersection at this point. So what happens now, let us say this is our this function. Now, suppose if I choose my starting point x naught here, then what happen? I can find out the value of f of x naught, right? G of x here. Then again, we can find out the value. This is our new value x1. So by doing this, what happen? We can come to this point. Suppose in the second diagram, what I want to show you, this is our root. If we start using our this initial guess point outside this, therefore this will go diverse like this. So in this case, what happen? We can convert to the requirements. So in this case also, choosing the starting point is very important, right? So now, so this one very simple here. Simply you read x naught. Okay, you choose a starting point from here, and number of iterations. Why you choose number of iterations? Just to stop the iteration, right? Just to come out from the loop. Then what happen? I find out g. Okay, you have to calculate g first. Then substitute the value of x naught just to get the new value of x1. Okay, then continue this for some loop. Then assign the value of x1 to x naught. Okay, new value, we are going to assign to all value. Then calculate this again. So how long we are going to proceed until the relative error is less than the allowed error. Then stop it. Okay, this is very simple, this is very straightforward. Now, how to implement in Python? Yeah, what happened here? I try for this for we can use for algebraic equation also, right? Now, okay, now the given equation can we write like this? F of x will be e to the power minus x minus 2x plus 1. Okay, this is my f of x. Now my g of x will be how much? As I have converted to like this 1 plus e to the power minus x divided by 2, right? So now I got f x and gx. Now from the given x, we calculate this g. So what I do, I use here. Okay, simply what I do, I calculate g of x, then assign x1 to x naught, then increase like this. And see, what happens? I just give one condition. If the number of steps is greater than the specified number of step loop, then you come out from the loop. Otherwise, what happens? You check this. Okay, this is the way. So what happens? Yeah, what is n? Now I will show you. What is n? N is the maximum number of steps. Suppose I want, in this case, what I am saying that I want to continue for 20 times, 30 times, I have to mention it. Now, say not up to 30 times. If we cannot convert to this root, then what happens? We can come out from this. Now, let us run this program here. You see here. So now, initial guess minus 1. So what happens? Say 0.001. Now, suppose let me say 20. So what happens? I just mentioned 20 here, right? But after I calculation, just come out from here. Okay. So this is our root. Now suppose sometimes if this iteration, if we cannot get our root within 20 times, then this will come out from the loop and we will get a message. What kind of message? Like this. Require not conversion like this. Suppose in the same program, let me show you again. Initial guess minus 1. Okay. Now either 0.001, something like this. Then now maximum step, let me say 3. Because as we know that this will continue up to 8 times. Just if I mention 3 for happen, this will give a message. See here, not conversion, like this. So this is again, as I told you, this is the way how to terminate our this program, how to terminate our this loop. So same thing what happen, you can use this idea in your this Newton Raphson method also. Okay. Instead that suppose here, suppose let us say this condition is true. So what happen? I am just telling you different methods. You may be thinking sometimes I use while, sometimes I use false, sometimes while true, like this. Many conditions are there. So this is another way. Well, this is like I define true. Then why I am doing like this? Cannot I write true here directly? No, because here I want to change my condition here. Okay. So in this way, you can implement your program in different ways. So what I do, I am just trying to explain you there are many ways for writing programs. So this method, suggested approach method, international method, okay, second method, they will have different methods. Okay, yeah, program will be different. Or if you know better than this, then you can implement it your own option, no problem. ಅದನ್ನ ಸೀದ ಅಪ್ಪಗೆ ಮೆಥಡ್ ನೋಡ್ರೆ ಅದನ್ನ ಸೀದಾ ತೋರಿಸಿ ಕೈನೋ sige function si aina test tawisi for given function aina takuru gini ko adana khande can we try for other functions for yes suma function ko madi x to minus plus y shampoo madi can we try it? Yes, you can try it. So suppose here another way here so fine adana sida yam negre ko yam negre adana you can try 3 or 4 questions. ಅದನ್ನು ನೀವು ತುಂಬ ಗೊತ್ತಾಗಲ್ಲ ಎಲ್ಲರಿಗೆ ಹೇಳೋಕ ಈ ನಿಮಗೆ ಅಟೆಂಡೆನ್ಸ್ ಲೋಗಿಗೆ ಈಗ ಅಂದ್ರೆ ಏನಿದೆ kana ಉತ್ತರ ಏನು ಗೊತ್ತಾ ನಿಕೋ ಅದನ್ನ
Sir,
ಅದು ಹೌದು
kung si tawag method na initial value choose tawag say convert tawag divert tawag di problem do lakna ba kung graphic yung choose tawag sir.
ಅದು ಯಾಯಿ ಜೊತೆ ಅದು ಅಪ್ಪನ generalization ಇವ ಈ ತರದಿ ಅದು ಯಾದಿರನ any question ಬಿನ ತಂದ ನಮಗೆ ಪ್ರೋಗ್ರಾಮ್ ನ ಕೊನೆನ ಕಂದ ಅಪ್ಪನ ಮೆಸೇಜ್ ಸಪೋಸ್ ತೌದರದಿ ನಮಗೆ ಅಪ್ಪನ ಕ್ವೆಶ್ಚನ್ ಕುಲ್ಲ ಪಠಾ ಚಲೈ ನಮಗೆ ಪ್ರೋಗ್ರಾಮ್ ಕರ ತರ ಕನ್ವರ್ಟ್ ತರೆ ಕೊ ನೇನೇವ ಅಪ್ಪನ ಇದು ಬಿಗಿನರ್ ಗಿ ಓಯ್ನಾ ಅಪ್ಪನ ಗ್ರಾಫ್ ಶೀಟ್ ko ala si root lay lay ka ko ko problem ko any given equation nಮಗೆ di ಅಪ್ಪನ ಈ ಪ್ರೋಗ್ರಾಮ್ ನ ಯಾಕ ಫೋಕನಿನ ಅದಿ ko ne hapta program iba tamda amak yadidನ ko ꯅꯣꯏꯃꯛꯀꯤ ꯏꯒꯗꯕꯅꯦꯕ ꯑꯗꯨꯅꯅꯦ ꯍꯥꯏꯅ ꯑꯗꯨꯅ ꯅꯣꯏꯃꯛꯀꯤ ꯏ ꯍꯥꯏꯇꯥꯔꯗꯤ ꯑꯩꯈꯣꯏꯅ ꯉꯁꯥꯏ ꯍꯥꯏꯔꯤꯕ ꯀꯟꯗꯤꯁꯟ ꯃꯌꯥꯝꯁꯦ ꯅꯣꯏꯃꯛ ꯌꯥꯎꯍꯟꯕ ꯗꯔꯀꯥꯔ ꯂꯩꯌꯦ ꯑꯗꯨꯒꯤ ꯋꯥꯅꯤ ꯍꯧꯖꯤꯛ ꯑꯩꯈꯣꯏꯒꯤ ꯕꯤꯒꯤꯅꯔꯒꯤ ꯑꯣꯏꯅꯕꯨꯗꯤ ꯀꯩꯁꯨ ꯀꯥꯏꯗꯦ ꯅꯪ ꯍꯥꯏꯗꯣ ꯑꯗꯨꯃꯥꯏꯅ ꯏꯕ ꯌꯥꯏ ꯀꯩꯝ ꯀꯥꯏꯗꯦꯕꯀꯣ ꯑꯗꯨꯒ ꯑꯩꯈꯣꯏꯅ ꯍꯌꯦꯡ ꯑꯦꯅꯤ ꯄ꯭ꯔꯣꯒ꯭ꯔꯥꯝ ꯑꯩꯈꯣꯏ ꯏꯔꯛꯄ ꯃꯇꯝꯗꯗꯤ ꯑꯩꯒꯤ ꯄ꯭ꯔꯣꯒ꯭ꯔꯥꯝꯁꯤ ꯁꯤ ꯈꯛꯀꯤ ꯏꯕꯅꯤ ꯑꯗꯨꯒꯤꯗꯤ ꯌꯥꯔꯣꯏ ꯍꯥꯏꯕꯗꯤ ꯌꯥꯗꯕꯅꯤꯅ ꯄ꯭ꯔꯣꯒ꯭ꯔꯥꯝ ꯑꯩꯈꯣꯏꯅ ꯏꯔꯤꯉꯩꯗ ꯖꯦꯅꯔꯦꯂꯥꯏꯖ ꯇꯧꯕ ꯀꯥꯟꯗ ꯑꯗꯨꯗꯤ ꯑꯣ ꯁꯤꯗꯗꯤ ꯁꯨꯃꯥꯏꯅ ꯂꯥꯛꯍꯟꯕ ꯌꯥꯏ ꯁꯤ ꯂꯥꯛꯑꯒ ꯃꯦꯁꯦꯖ ꯁꯨꯃꯥꯏꯅ ꯊꯣꯛꯂꯛꯄ ꯌꯥꯏ ꯍꯥꯏꯕꯒꯤ ꯋꯥꯈꯜꯗꯀꯣ ꯑꯗꯨꯒꯤ ꯑꯗꯨ ꯌꯥꯅꯕ ꯏꯕ ꯋꯥꯅꯦ
Hello sir, makokta kuna function define tawdo. Adadi kuna particular or define tawdo na function do. Adaju koi ibang function mo masina raga kana tawdo hadi console do enter tawdo ya.
Ya adu da kedo ne ki wali do de du shey adu fa da ko da shey so ya anu dai ni diga ka wala ko adu su tawdo ya na any da function ngai ni ya ko adu ne hai ko da ko di da ma da kan ma du i hai kan da ko na to ana na te ke da ma chale na ko te ke da chale kan da na ni si pa kan ni community da ka do ko ya yes why do na ai ni ro ba ta se di se approximation any function mana ya ni transitive ke algebraic ke mana so to me ta do ri ko hai me na verify ta ja hai ta di me na ni community na ni achang ne ba adu na my contribution from this kelvin ke to adu ma ta ne adu open source hai je ne akan hang share to ma ta ne adu ya ke su bai de adu na maru na we Python da to put jam ame ko website design to ba server manage to we we community ame scientific ne ke wa le ko aduna akoi te ku sem ya ko ma ta ku ye developer to na mo material pamon ko ga le ko good team ni lo sa phong ne ta na san sai shin du ya ken khai din ko to we da am to bi ya aduna Python ge advantage da ti ma ya me ga ma ya ne ko adu pa ni da ya me ko na ni git hab kai na ma ge yam nei ne ko we community ne am ye na wa sha ma ಅದು ನನಗೆ ತಿಳಿಸೋಣ ನನಗೆ ಅದು ತರಬೇತಿ ಶುಕಾಯಿದೆ ಆಯ್ತು ತಕ್ಷಣ ಅದು ಅದನ್ನು ಆಯ್ತು ತಗೋಬೋದು ಏನಕ್ಕಾಗಿ ಇದು ನನಗೆ ಬೆಸಿಕ್ ಬದಲೇ ಬೇಕು ಬೆಸಿಕ್ ಹೇಳಕಾರಣ ಏನು ತರಬಹುದೇನೆ ನಮ್ಗೆ ಐದು ಐಡಿಯಾಸಿ ನಂಗೆ ಫಂಕ್ಷನ್ ಇನ್ನೇನು ಬರೋದು ಕೀಬೋರ್ಡ್ ಕೌಶಲ್ಯ ಪಾಲನೆ ಕೋ ಅದೈದು ಇದು ತಗೋಗ ರೂಟ್ ಸಿನಿಗೆ ಹಾಕೊಂಡು ಕೋವಿಡ್ ನಾಳೆ ರೂಟ್ ಸಿನಿ ರೂಟ್ ಅಮದಿ ನಾಳಿಂದ ಸಪೋಸ್ ಕೊರೋನಾ ರೂಟ್ ಅಹುಮ್ ಹೇಳೋ ಅಹುಮ್ದ ಅಮನ ರಿಯಲ್ ರೂಟ್ ಮೇಲೆ ಅನಿ ಇಮ್ಯಾಜಿನ್ ಉಳಿಗ ಇದನ್ನು ಖಂಡಿ ಇಮ್ಯಾಜಿನ್ ಗಾಯ ತೊಂದಿ ಯಾಕೋ ಕೊತ್ರ ಫೌದ ಹಾಬದಿ ರೂಟ್ ಅಮದಿ ರಿಯಲ್ ಒಳ್ಳೆ ಕೋ ಅದೇ ಪಿಯಾರ ಲಾಖನೆ ಇಮ್ಯಾಜಿನ್ ಪಿಯಾರ ಲಾಖನೆ ಅನಿ ಇಂದಿ ಇಮ್ಯಾಜಿನ್ ಉಳಿಗಾನ ಮೈ ತೊಂದಿ ಜೊತೆ ಶುಕಾಯಿದೆ ಕೋ ಅಯ್ಯ ತಾಯಿ ಸುಮಗಿ ರಿಯಲ್ ಕ್ಲೀನ್ ಇಮ್ಯಾಜಿನ್ ಗೆ ಶಿಯಾ ತಗೋಯ ಇದೆ ಕೋ ಅದನ್ನ ಹಾಯ್ ಬರಂಗ ಪ್ರೋಗ್ರಾಮ್ ನೀವು ತಂದ ಲೋಡ್ ಸುಮಗಿ ಒಂದು ಫೈಟ್ ಬೆಸ್ಟ್ ಆ Question ya bo gelin gen tadi ko ya
Yeah sir.
ꯑꯇꯩꯗꯨꯗ ꯑꯇꯩꯁꯨ ꯈꯔ ꯀꯣꯏꯁꯟ ꯍꯪꯉꯨ ꯀꯩꯅꯣ ꯑꯇꯩꯁꯨ ꯒ꯭ꯌꯥꯟ ꯇꯥꯔꯤꯕ ꯇꯥꯗꯕ ꯇꯧꯔꯤꯁꯤꯕ ꯑꯩ ꯃꯊꯥ ꯁꯥꯔꯦꯅꯦ ꯈꯪꯗꯤ ꯈꯪꯉꯤꯕ ꯅꯠꯇ꯭ꯔꯣ ꯑꯗꯣ ꯍꯧꯖꯤꯛ ꯑꯩꯅ ꯇꯧꯗꯣꯏꯁꯤ ꯀꯩꯅꯣ ꯑꯩꯅ ꯊꯥꯔꯤ ꯄ꯭ꯔꯣꯒ꯭ꯔꯥꯝꯁꯤꯡ ꯃꯁꯥ ꯃꯁꯥ ꯌꯦꯡꯉ ꯇꯣꯛꯀꯅꯨꯀꯣ ꯍꯧꯖꯤꯛ ꯑꯦꯁꯥꯏꯟꯃꯦꯟ ꯂꯥꯛꯑꯒꯅꯤ ꯑꯊꯨꯕꯤꯗꯀꯣ ꯑꯗꯨꯅ ꯑꯦꯁꯥꯏꯟꯃꯦꯟꯗꯨꯒꯤ ꯃꯇꯨꯡ ꯏꯟꯅ ꯑꯩꯅ ꯇꯧꯗꯣꯏꯁꯤ ꯀꯩꯅꯣ ꯉꯁꯥꯏꯒꯤ ꯍꯥꯏꯔꯤꯕ ꯑꯩꯅ ꯄ꯭ꯔꯣꯒ꯭ꯔꯥꯝ ꯃꯣꯗꯤꯐꯥꯏ ꯇꯧ ꯍꯥꯏꯗꯣ ꯑꯩꯈꯣꯏꯒꯤ ꯔꯤꯖꯅꯔꯦꯁꯟ ꯃꯦꯊꯠꯅ ꯀꯩꯗꯧꯕ ꯉꯁꯥꯏꯒꯤ ꯇ꯭ꯔꯥꯟꯁꯗꯦꯟꯇꯦꯜ ꯏꯀ꯭ꯋꯦꯁꯟ ꯁꯣꯜꯕ ꯇꯧꯕꯒꯤꯗ ꯏꯕ ꯀꯩꯅꯣꯗꯣ ꯑꯗꯨ ꯈꯣꯠꯄꯒꯨꯝꯕ ꯀꯣ ꯑꯗꯒꯤ ꯁꯦꯀꯥꯟ ꯃꯦꯊꯠ ꯁꯤꯖꯤꯟꯅꯕ ꯈꯣꯠꯄ ꯃꯌꯥꯝꯁꯤꯗ ꯅꯣꯏꯅ ꯈꯔ ꯃꯣꯗꯤꯐꯥꯏ ꯇꯧ ꯇꯥꯔꯦꯀꯣ ꯗꯥꯏꯔꯦꯛ ꯑꯩꯅ ꯄꯤꯔꯤꯁꯦ ꯐꯣꯟ ꯇꯥꯔꯦ ꯇꯧꯒꯅꯣ ꯑꯩꯅ ꯄꯤꯔꯤꯁꯤꯗꯤ ꯏꯚꯦꯟ ꯐꯪꯁꯟ ꯈꯔꯁꯤ ꯈꯛꯀꯤ ꯋꯥꯅꯦꯕꯀꯣ ꯑꯗꯨꯅ ꯑꯇꯣꯞꯄ ꯃꯈꯜ ꯃꯌꯥꯝ ꯁꯤꯖꯤꯟꯅꯕ ꯌꯥꯏ ꯅꯣꯏꯒꯤ ꯄ꯭ꯔꯣꯒ꯭ꯔꯥꯝꯗꯨꯅ ꯐꯣꯟ ꯇꯥꯕ ꯇꯥꯗꯕ ꯇꯥꯗ꯭ꯔꯗꯤ ꯀꯃꯥꯏꯅ ꯏꯅꯔꯗꯨ ꯀꯃꯥꯏꯅ ꯂꯧꯊꯣꯛꯀꯅꯤ ꯃꯣꯗꯤꯐꯥꯏ ꯇꯧꯅꯤ ꯀꯥꯏꯗꯀꯣ ꯑꯗꯨ ꯂꯣꯏ ꯂꯥꯛꯀꯗꯣꯏꯅꯦꯕ ꯑꯗꯨ ꯃꯌꯥꯝꯗꯣ ꯁꯤꯒꯤ ꯄꯤꯔꯤꯕ ꯄ꯭ꯔꯣꯒ꯭ꯔꯥꯝꯒꯤ ꯒ꯭ꯌꯥꯟ ꯇꯥꯗ꯭ꯔꯒꯗꯤ ꯎꯄꯥꯏ ꯂꯩꯇ꯭ꯔꯦ ꯀꯣ ꯑꯗꯨ ꯆꯤꯟꯐꯥ ꯆꯠꯄꯗꯗꯤ ꯑꯇꯩꯗꯗꯤ ꯌꯥꯏ ꯁꯤꯗꯤ ꯌꯥꯔꯣꯏꯗꯣ ꯆꯤꯟꯐꯥ ꯆꯠꯂꯨꯅꯤ ꯑꯩꯅ ꯀꯣꯏꯁꯟꯗꯨ ꯃꯣꯗꯤꯐꯥꯏ ꯇꯧꯊꯣꯛꯀꯅꯤ ꯑꯗꯨꯝ ꯁꯥꯔ ꯁꯥꯔꯦ ꯅꯠꯇ꯭ꯔꯥ ꯑꯗꯨ ꯉꯁꯤꯒꯤ ꯂꯣꯏꯁꯤꯜꯂꯁꯤꯀꯣ ꯍꯌꯦꯡ ꯑꯃꯨꯛ ꯊꯦꯡꯅꯔꯁꯤꯀꯣ